the next video for the playlist is actually waiting on components to come in the mail. And I didn't have much else to do this afternoon, so I thought maybe I can make some other videos that are at least kind of related. And then I thought there was something on my mind. We'll talk about that here in just a second, why it was on my mind. But something that has shown up in every video, and we haven't really talked about it in detail, so I thought, why don't I put together a video? I will try to talk quick in all these things, so that way it doesn't take too much. It's shown up in every video, and it's kind of an important part, so why don't we take a video and go ahead and talk about that. So to describe it, or lead into it, I'm going to use a UML use case diagram. UML is Unified Modeling Language. That's the international standard of communication for IT stuff. A pictorial-based language, so that no matter what language we speak, we convey our information through pictures, and then we can tell what's going on there. So a use case is the picture that shows our user. So stick name for our user, and then whatever IT device we're looking at. It might be software, it might be a single device, it might be a combination of things, but the IT part and the user part. And, well, whatever we have, it's probably going to get some input from the user. Some sort of input coming in from the user. Then, let's just refer to it as a device. Then that device is going to do some sort of processing, right? Depending on that input, I'll try to keep it kind of simple here. 2 different processes could happen, not but a couple processes. So depending on the input the user gives us, it's going to run through one or the other processes. And then the whole point that the user gave input for, right? The user probably sent in that input because they wanted the output. They want to get something back. They want to know what the result of that processing is. So that's our topic for today. Something that the rest of this playlist is kind of taken for granted. So let's talk quickly about outputs and just kind of go over some of those. We've seen some, right? Most of the stuff so far in these examples, trying to get the simplest case. We just need to see if the output is on or off. You know, if it's turning the next component on or not in a long chain of components, or is there something or is there not? So most of them so far, we were able to do with an LED. Simple starting point. Hook up some voltage, positive voltage coming into an anode, come back out the cathode to ground, and it comes on when we send the voltage. But I just use those 2 technical terms. It's introduction level, so I've been trying to avoid technical terms. Those 2 I don't like in particular, so I'm going to talk here in just a second about why I don't like those. But we're going to need them if we're talking about LEDs. We're going to need those technical terms, so I'm going to mention them a lot. So I'm going to talk about what I'm going to go over a way to remember that. How to keep track of which one's which. And real quick here, before we start talking about the technical terms, the reason outputs were on my mind is, along with teaching, I also tutor. Yesterday was the last day of the semester. I was scheduled to tutor for 6 hours, and being the last day of the semester, most people had already taken their tests and everything, so I didn't see a single person in the 6 hours I was there. And one of the things I did, if it shows up here, is I designed out a waterfall that will display as a clock. Opening and closing valves in very precise sequence, so that as the water falls, it looks like a 7-digit display. And make a clock that way. I thought it might look really nice. At least I had really a lot of fun putting it together, but because of that, outputs were on my mind. And, well, the pieces for the next video are still on their way in the mail, so let's do a video on outputs, because thus far, we've always just taken that for granted, right? We just said there's an output, and when we need to display it, I throw a LED in the simplest case example. But let's look at some outputs in general today. So let's talk about those technical terms. Anode, anode and cathode. So we're going to need to use those here in a moment when we get to a scene talking a lot about LEDs and different kinds of LEDs. So first off, the reason I don't like using these, and not just because this is supplemental material from introduction class, so I've been trying to minimize the technical usage. Even if I'm talking to other people that know electricity, I don't like to use these two terms. The reason for that is these are chemistry terms. They're chemistry terms that electricians adopted. So cathode is where reduction occurs. That, if you have chemistry, that means we gain electrons. Electrons, and if we're gaining electrons, that's going to come from an acidic chemical reaction. So we gain electrons from an acid. So the cathode side is the one where we gain electrons from the acid, the anode's the other end of that. And personally, I don't like to memorize things. I like to understand the process so that when I need it, I can think it back through again. I just think it through and figure it out again, and don't have to waste a whole bunch of energy memorizing things. So one note about electricity is it's labeled backwards. This goes all the way back to Ben Franklin. Throw a picture here. So when Ben Franklin did his experiments a few hundred years ago, one of the ones where the labels came from, he had a glass rod and a silk handkerchief. Obviously, it was thorough experimentation, so it wasn't always a silk handkerchief. Usually a glass rod or something similar. Getting into physics a bit advanced, but this one was always something stiff, and this one was always something flexible in order to get the produced results. So most often a silk handkerchief or a rabbit fur on one side. Well, when he was messing around with the electricity, we get the polarity, and positive and negative are attracted to each other. So what he observed time after time after time with different materials, talking about a glass rod and a handkerchief here, the silk handkerchief would move towards the glass rod. So that's the way he labeled it. We usually label things going from the positive to the negative. So that's become known as conventional notation. It goes from the positive to the negative. Well, eventually we learned that was incorrect. You know, his experiments were all thorough and everything, but once we knew more about quantum mechanics, we learned it actually goes the other way. And what was happening here wasn't that the silk handkerchief was trying to move, it's that the glass rod, which was stiff, was trying to move so hard that it caused the other one to move. But when we first figured it out, this would be the early 1930s, attempts were made to change to correct the labeling. And very promptly, a number of people were killed in accidents. So we went back to the old labeling, and since then, it's just students are informed the labels are backwards. Be careful, so be aware of that, because we don't want to do that again. And if you're ever dealing with a circuit from the early 1930s, be careful, because it may have fallen into that attempts to correct the labeling. But conventional notation, what I will always go with, things move from positive to negative. So on one side, we're gaining electrons. Those have a negative polarity. So this is the side gaining electrons. So you can track it through that way. But again, what I don't like about these terms is they're chemistry terms. The cathode means where reduction occurs. So let's trace through the power as it comes to this LED on our setup here. I'm in southern Indiana, so that means power is coming from a coal plant. There are some hydroelectric plants, but they're bigger coal plants. So I'm going to assume it's coming from the coal plant. So there we're burning a pile of coal to boil some water, which turns a turbine and a generator and create some electricity, which is then going to flow down some lines as alternating current and get to my house. And once inside my house, I'm going to plug up my laptop. That's supposed to be a picture of a laptop. And when I plug it up, it switches from AC to DC current. There, comes over to the laptop. I don't think my laptop even has a battery in it right now. I always run off the cable. So, power plant to the house to the laptop. Then in the example so far, mostly sending that out to a microcontroller, even when using that like a battery. And then took up the positive and negative side of the microcontroller. And this is why I don't like those terms. Because in this setup, burn coal to boil water, come down a line into my house, into the laptop, into the microcontroller. So which one of those is getting electrons from an acidic reaction? The old batteries used acid, and that's how the old batteries worked. But that's why I don't like those terms, because they don't apply to how we typically use this. Gaining electrons have a negative charge. So if we're gaining electrons, that's our negative side. So the cathode goes to the negative, and the anode goes to the positive. And what I always remember is just the alphabet. There are a number of ways to remember this, but we have our anode and cathode. So one starts with an A, one starts with a C, obviously. So in the alphabet, A goes to C. So that's how I remember it. Positive goes to negative, A goes to C. So we put the anode to the positive side and the cathode to the negative side, and it's probably going to show up somewhere. So our symbol for this in schematics is a little filled-in triangle. So we have a filled-in triangle with a line afterwards. So this side is the anode, and this side is the cathode, when we see that in schematics. So just a couple of quick points about these technical terms that are going to be used and why I don't like using them. There is no acidic chemical reaction in this process that I draw power from 90% of the time. So chemistry terms do not apply here. But they're the technical terms. Those are the terms that should be used when talking about this. So I need to use them for today's thing. So just think about the alphabet. A goes to C, positive goes to negative, A goes to C. And the symbol looks like this. So like the triangle is the anode and the vertical line is the cathode. Those are going to come up and when we talk about this next section. Okay, so that brings us up to the main content for today, which is essentially just going to be a list of different outputs. For simplest case examples, most of the outputs are going to continue to be a simple LED. But since that's the one we've seen so far, light emitting diode, let's look at sort of an assortment of different varieties on light emitting diodes. And I think I forgot to mention a minute ago, I specifically drew the picture that way to say something about it and then forgot. Unless they've been trimmed, if you just have a simple LED, just a basic single color on or off, one of the leads will be longer than the other. The longer lead is the anode. I drew that picture to say that, and I think I forgot to mention it. So, but we don't always have to use the simplest LED. There are some basic ones that are much more useful than just a single LED. Basically, several LEDs put together for us. So let's go take a look at a quick sampling of combinations of LEDs already put in a nice order for us. Okay, so here's some examples. So starting with just a simple LED, we've seen that a couple times. And like I mentioned a moment ago, one of the leads will be longer than the other. The longer one is the anode and the shorter one is the cathode. So when hooking that up, put the shorter one going back to ground and the longer one coming out. So on all of these resistors are plugged up to the cathodes. I did that to keep them straight. So on a basic LED, that's straightforward. This one you can see it's one side's cathodes, the other side's going to be anodes. Here they're organized kind of in the middle. We'll talk about them in turn. This one you'll notice is a mess. We'll talk about that in a moment. So to start with, just a simple LED. So I'm going to plug this into the positive voltage somewhere and just bring this over here and connect it. So you can see whenever it makes connection, it's going to flow through and do that. The next one here, this is referred to as a bar graph, an LED bar graph. So it's basically 10 LEDs. So we can use them any way we want, but typically it shows output levels. So if we just start plugging them in, you can see it's 10 separate LEDs organized in a way that we can, kind of show a level going up and down with that. Very straightforward, cathodes on one side, anodes on the other, and then we just form the connections. And for all of these, really, there's 10 outputs. We wouldn't want to use 10 pins on a microcontroller to control that, so we'd probably use shift registers. Remember, a shift register, it controls 8 outputs with one input. So a serial communication input goes to 8 outputs. And you might be thinking, if you watch that video, but didn't it take 3 lines? And yes, it took 3 lines, but 2 of those were clock signals. And clock signals synchronize things, so those clock signals are going to be used at, say, every register. So if we had 20 registers, we'd need 20 serial lines, but we would use the same clock signals to synchronize every single register. And most of our components need synchronized together, so those clock signals can be used elsewhere too. So the clock signals are just kind of something we have to have if we have a bunch of components. But basically we can control 8 outputs with 1 input using registers. But again, today, just kind of pointing at the devices. So we can typically, for showing levels, as we, like you've probably seen with speakers on a sound system before, on radio or something, it's going to highlight a different level amount. But there are other uses for it. The next one here is a 7-segment LED. So, like the name implies, 7 separate LEDs to make a number, right? These 3 down the middle, and then these over here. And there's actually an 8th LED on most of them, the little dot in case we need a decimal point afterwards. So on this one that I hooked up, there's 2 common cathodes, so I have those coming back to ground, and then each one of these LEDs gets its own anode. So if I bring the wire in here, if I can put my hand someplace where it's not going to be in the way, maybe if I bring the wire over here. Yeah, I'll run it from there. Then hopefully it won't be in so much of the way. Then as I connect each different output here, you can see each of the 8 pins on there, a different LED comes on. And then 4 more down here. Oh, my hand's in the way. So 4 more down here. Whoops. And that turns on each LED one by one. And let's look at the back of those real quick. Not sure why my computer's making noise there. So on the back of this bar graph, if I pull that out real quick. Didn't leave myself much room to take those out. So you can see just 10 pins. And they're the same size, so we can't tell by looking which side is the cathode and which one the anode. So you actually have to check, which means just plug one of them up to ground and the one across up to the positive and see if it comes on. If not, flip that and try again. one way or the other should come on. So I'll plug that back up. Then the next one here, whoops, I plugged that in the wrong spot. Plugs up there. So on the back of the 7-segment LED, you'll see 10 pins. And again, this one had a common cathode, but it might have a common anode. So you just have to check. Put that middle pin to ground and then plug up one of the other ones and see if something comes on. If that doesn't work, put the middle pin to the positive rail, plug up one of the others to ground to see if it comes on. It'll come on one way or the other. So that's how we control those. And I'll go ahead and pull this up because there's going to be a lot more talking about this one. So here we have a big matrix of LEDs. So an 8x8 matrix, which we can control with rows and columns. And then we have 16 pins. So 8 of them are anodes, 8 of them are cathodes, but they are not as nicely organized as these. What this did is they optimized the wiring internally, which left these pins as kind of a mess. So as you can see from the way it's hooked up here, I put resistors on all the cathodes, and they're kind of scattered all over the place. So let's pause real quick here and look at something on the computer to kind of tell which ones are anodes and which ones are cathodes. Okay, it's the first time it's shown up when making these videos. It may not be the first time in the playlist, but every electronics component has a standard reference material called a data sheet. So if you just take the part number, in this case I took 788BS and put that in Google, one of the top results should be the data sheet that gives you all the information about it. So to find our pins, they're optimized internally, so when we look at it from the outside, it doesn't make much sense. The pins will go in order counterclockwise. So one thing we do know is that pin 1 will be in a corner. So what I did is I just picked one of the corners and guessed that's pin 1. So from there, I counted around. We can see pin 1 goes to an anode, and the cathode connected to it would be pin 13. So I picked a corner, counted around to what should have been 13, stuck a resistor back to ground, and sent 5 volts to pin 1 to see if the correct row, so column 1, row 5, came on. It did not on my first attempt, but it did on the second. So then I picked another corner, repeated that process, and it worked on the second corner. So once you find pin 1, then you just count around and check the data sheet for which ones are anodes and which ones are cathodes. Cathodes head back to ground, anodes bring the positive voltage in. So do have to actually check that on these because it seems like there's not much rhyme or reason when we're looking at the outside after it was optimized for the inside. So let's go back to the circuit. Okay, so to see that in action, I'm going to stick this wire in the hot rail, and then I'm going to hit each one of those anodes in turn. So pin 1 here, you can see turns on that row. And then we would multiplex through those columns, or multiplex through the rows. There's another video about multiplexing. I probably could have used this component for that video. But you can see pin 1 turns on that row of LEDs. And then when we multiplex through it, we can make it set up the pattern we want. Then pin 2 was an anode. It's going to turn on that row. Pin 3 and 4 are cathodes. Should be a pin 5 here. Yeah. So pin 5 turns on that row. Then 6 and 7 and 8 will turn on rows of LEDs. Then down here, pin 9 turns on a row. 10 and 11 are cathodes. 12 turns on a row. 13 is a cathode. So then pin 14 turns on the last row. So we can set up the multiplexing, and we have an 8x8 pattern of pixels basically. And that'll lead nicely into the next thing we're going to look at, because that's kind of like how we set up pixels on a screen. So 8x8 row of LEDs that we can control any way we want just by multiplexing through some columns and rows. Turn on the matrix for the row and column the LED for the row and column we want in the matrix, and then make any pattern we want show up on that. So that's just some alternatives. They're basically just LEDs. They're just already set up in some common useful formats that we can use. So essentially there, we're still just turning on an LED, well, multiple LEDs in a more useful format, right? Instead of just on or off, we can put that in a way that conveys some sort of information to a user. And it's like doing more with our outputs. And that's kind of what this little video is to address. Because everything in the playlist is simplest case examples. So we just need to see that there is an output. We just need to see if the output is on or off. And usually just a single LED is enough to indicate that in the simplest case examples. But hopefully you can expand that up to what's not the simplest case example. And we're covering this for more complicated examples, so I thought I'd kind of address some of these things and see that there are other options. Once we get to that final part where we turn on an LED, turn on a light for most everything in the playlist, we could do more. We could, instead of turning on an LED, we could turn on a 7-segment display and show a number. Or we could turn on the bar graph and see some sort of level there. Or put a symbol on the matrix, right? We can use that 8x8 grid and choose which ones are on to put a letter, a number, a smiley face, some sort of picture there. And that last one kind of leads into the next thing nicely, because then, that should remind you of the rows and columns from when we talk about screens. So maybe the next step to talk about an output would be really useful output, some text output. I'm going to put text output, obviously, well, text to graphical. Text and graphics. Convey some useful information back to the user, maybe in the form of a sentence so they can see what's going on, or some sort of picture to indicate things. So let's look at a couple of examples of those real quick. And so here is an OLED screen, again just displaying some words, and I got some random graphics showing. The graphics are a little bit better, so I went ahead and drew a small clock on there, which is completely random. It just picks a random hour and a random minute and throws those up there. And OLED is OLED, which stands for organic LED. And as far as chemistry goes, organic just means the molecule contains carbon. So as opposed to the traditional LEDs, which just have an anode and a cathode, an organic LED has two more pieces shoved in between the anode and the cathode, which contain carbon and make it's generally taken the light from them looks a little bit better to humans, because it's a carbon-based molecule makes, or just the word organic. Organic blends, seems like a more natural lighting to humans. But again, we're multiplexing this screen, so we turn on all the pixels in a row and flash through the columns really quick so that it looks like one single picture. This particular one, this screen has 128 pixels across and 64 pixels down. And then we just control which ones we have. And on this particular one, the first 16 pixels are yellow and the rest are blue. To help organize the data, it's showing a little bit better. But there's still, like the LCD screen, there's not a lot of color option on it. Just a way to show some text and graphics. Okay, those little screens can convey a little bit more information, but the key point there is probably little. Right? A big screen would be better. So that kind of leads directly into last one we're going to show examples of and talk about some. And to categorize it, I decided to just maybe put input elsewhere. So the last kind of category for this video of things that we could do with our output is just have that output as input elsewhere, such as the regular PC screen. So let's go look at a couple examples of that and talk about that. And hopefully this video is helping to see that, you know, all the simplest case things in the playlist, we're just turning an LED on or off to see if we have, to see that it worked. But hopefully it can be expanded. It makes sense that those simplest cases expand up to more reasonable cases where we need to do more with our output. And, you know, maybe multiple LEDs to get a better indication, like the 7-segment displays and show a number, or send some sort of text and graphics to a OLED screen. Or we can just use our output as input someplace else. So let's go look at an example of that. So the next option for a screen is just to use your regular one. I'll upload this real quick. Hopefully it won't take long. It's a little bitty script. You can see the whole thing here. So I just set up a blank string, started the serial communication, the 115,200 baud rate. So that's how many times per second it will send can send communications. Then here it just checks and see if there's anything on the serial. If there's something coming down the serial port, it's going to put whatever's there into the string and then kind of process through it. Just two examples, just a hello world here. So right off the bat, obviously the IDE has a monitor for this. So if I, whoops, not the plotter, click the wrong thing. If I open the serial monitor, set it the right baud rate, then I can just pass in those commands. Say hi, brings back hello world, or what was the other one? Test. Yeah, and then it brings back that. So that works. We can see the words, but not a very useful one. Can't really save that without manually copying and pasting it. So a better option is what I have over here. So normally, well, obviously, any programming language can access the serial communication port. Normally, I do it through PowerShell because that's just the basic Windows 10 controls. So from PowerShell, I can get the data from a microcontroller and redirect that to any software running on my PC. But for the nature of this playlist, the people that will be directly given the links from me, students in my courses, are probably more familiar with Python. So I just did it in Python here. So just set up a serial communication port, and doing it through Python, the microcontroller has to reboot. So then I just delay for 3 seconds, and then I'll have this variable to access it from. So if I go ahead and run this, and yeah, I've never sat down and timed how long it takes that to reboot. My first attempt was 3 seconds. It didn't feel like that long, so I've always gone with 3 seconds, but I could probably do it quicker than that. And then once the command prompt comes back up, I already set up this variable to work with, so I can just pass in messages that way. So com, that serial communication variable, and then I'll write some data. And it has to be a binary string, so coming from Python, we have to put a lowercase b there to make it, to translate it into a binary string. And then we can just pass those commands. Say hi, and then that's going to go to them. So it's saying it sent 6 things, 6 bytes to the microcontroller. The microcontroller would have responded, and the next thing on the serial port should be the response. So you can see I send and say hi, and it responded with a binary string of hello world, which here includes the B because it's a binary string, not an actual string. And then it has a carriage return and a line break in it, but we can parse the data we need out of that. Same thing for the other one, com.write, a binary string that says test, and then a new line, because it didn't automatically pass in a line break. I forgot to point it out at the time, but you may have noticed it took a second for that to happen. And that's because it had to time out. It was reading until it hit the line break, and Python doesn't include line breaks by default. So when I passed this one in, the new prompt came up very quickly, and we can just read what's on the serial line. And there's our data with some other stuff, so we have to parse the thing we actually want out of it. But then we can use it in software on the PC. I just showed Python here because people in my courses are going to be more familiar with Python. There's a better chance of that. Typically, I would use PowerShell, just the basic Windows PC control, because then I can grab the data from the serial port and the device doesn't have to reboot that way. So it's quicker right off the bat. And PowerShell automatically includes line breaks. So don't have to worry about that. And PowerShell sends binary strings to serial communication. So don't have to manually convert those. So it's a little bit easier here. And then from here, I can redirect it to any software running on the machine. Just, redirect the data from the microcontroller directly into Excel to put the data in a spreadsheet or something. A little beyond the scope of this. The point of this is just to show that if we need a screen, we can just use our regular one as well. So let me pause the video and get set up for the next quick point about the regular screen. And the other way we could use the screen is maybe to plot out the data. So first off, I commented out most of the commands going back and forth and just printing a random number between 0 and 100 every third of a second. So again, the IDE has one built in, so you just need to look at that. Just open that, see it on your regular screen. Just plotting out a random number, but again, that's lifetime output, so kind of limited. It can be useful when we need it, but we can't keep it around. So for that, we might want to use some other software. And there might be better ways to do it. The quickest, easiest way I could think of, so I'll upload this. So here I just took what was there in the last scene and I added another command. If I type in next, it prints a number between 0 and 100. So again, to try and keep it simple, I'm just doing something simple in Python and going to use a MATLAB plot, and that seemed a simple example that any software that can plot out numbers would work for this. And hopefully the concepts here, just down here in the loop, the key point is this, again, just sending the line down the serial communication. So the X is printing out what pass we're on. Then we ask for the next number, and then read line, cast that binary string that returns into an integer. So that'll cut off the line breaks and the indication that it's a binary string, just get that as an integer. And then plot it on the thing, plot it on my a MATLAB plot. So if I run this real quick, again, we have to wait for the Arduino to boot up when we do it from Python. There are other ways that don't require that. We can see it just plotting the data out here. So a lot like the serial plotter, only here we're doing it in Python, so we could use this directly in our software. But hopefully the general idea there is getting across that anything that can draw a plot, we can do it and just use our regular screen instead of one of the little ones wired up specifically for our device. We can just send our data back to some software we're comfortable with using, such as Excel, which has quite a few steps, so it seemed a little overcomplicated for the example. But once we have it plotted here, we could save that graph, process numbers out of it, do all the MATLAB stuff. And the general idea, though, is our regular computer can access the data from the microcontroller as well. And that's just a very useful output, especially in what I'm saying and not just explaining there, because it's a little complicated, but send the data to Excel and then we have our output is a regular spreadsheet like we're probably familiar with. Okay, so that last little point I was making there, it is not complicated. The whole running the data from some microcontroller into Excel, but it is a lot of steps, so it doesn't really fit in a video where I'm trying to do the simplest case examples and get a lot of things here. But it does make a nice segue, since we can see that, it makes a nice segue into this next section. Because obviously we could store data once we get it, send it to our PC, just put it on the hard drive there. Or a similar thing, I have a little micro SD card reader here. Just put that in the device and our output just gets sent to storage. Is another option for output. That way it's still around and we can do stuff with it later. Or connected to sending it somewhere else, here I have a HC05, that's a Bluetooth chip. So we could just connect to a nearby device and send our data and use the software on some nearby device to process through the information that we're sending it. Or over here is an ESP8266, which is a Wi-Fi chip. So we could do the same thing with any device connected to the internet. Just send our data from the microcontroller and whatever inputs it's connected to, send it through the Wi-Fi to the internet, and then a device somewhere in the world connected to the internet can process through it for us. And obviously these could also be used as inputs, right? We could get a signal from the internet as our input for the device, or get a signal from a nearby device. Or we could put all our steps into a text file and just run through that text file in order for the inputs from storage or something. Lots of different options there. But just a quick pass here on different versions we have for outputs, right? We saw the little, along with the basic LEDs, some more useful setups of LEDs that combine LEDs into predetermined packages that we can use. Expanded that up into some small screens, or use the regular PC screen, or we can just connect wirelessly to other devices or store our output. There's a lot of choices of what we can do with the output. So all the examples in this video, we're just basically doing simplest case, turn on and off an LED for basically everything in the playlist to see if the output is on or off at the end after the simplest case version. But this video was just to quickly show there's lots and lots of choices of what we can do with our output. Once we have our output, we can use that as an input somewhere else and have a lot more functionality available. I just wanted to express that point somewhere, because everything in this playlist has that simplest case, and obviously we're talking about this stuff for more than just turning on an LED. So instead of turning on an LED, which is the simplest case of output, there's a lot of different things we could do.